Hello, in this session we will discuss about classical harmonic oscillator. In our past sessions we have discussed particularly in one dimensional box and particularly in three dimensional box quantum mechanical problem. So why we want to discuss harmonic oscillator problem? By discussing the harmonic oscillator problem, we can relate to the bond dissociation energy and the vibrational frequency of a particular bond. So if we understand a harmonic oscillator problem, we can find out the bond dissociation energy and the vibrational frequency of associated with particular kind of bonds. Before going into quantum mechanical harmonic oscillator, we'll first try to understand a typical or conventional classical harmonic oscillator. Then from that knowledge of classical harmonic oscillator, we'll derive our expressions for quantum mechanical harmonic oscillator, and from quantum mechanical harmonic oscillator, we'll try to derive the expression for frequency of bond vibration or the bond dissociation energy. So a classical harmonic oscillator, suppose there are two masses attached with a spring, and let the spring have a force constant x. Suppose mass m1 is a smaller mass, or the mass is less compared to mass m2, or mass m2 is a larger mass. Now if I stretch mass m2 towards right hand side, the spring force constant of the spring will be in the left, towards the left hand side. Means spring will try to pull back the mass m2 towards left hand side as I am applying the force, or I am trying to displace the mass m2 towards the right hand side. So what it means, the displacement and force, the force of the spring or the force constant of the spring act in opposite direction. So from our classical physics knowledge, we can say that restoring force of the spring is given as minus kx. What is k? K is called the force constant of the spring, and x is the displacement from equilibrium position. m1 and m2 are two different masses. The negative sign, why this force is associated with a negative sign? Because the force and displacement are in opposite direction. As I said, if the displacement is towards the positive x direction, the force will be acting towards the negative x direction, as I said from this right hand side and left hand side example. Then the one more important point to note is the magnitude of the displacement are not equal to their the magnitude of their displacement are not equal if their masses are unequal. Here the masses of the bodies, the m1 and m2, there are two bodies associated and their masses are unequal, so the displacements will be also unequal. Suppose for m2 the displacement is x2 and for mass m1 the displacement is x1. So if I apply the same force to displace both the particles or both the masses, the displacement associated with the masses will be different. The larger mass or the heavier mass will have smaller displacement, and the lighter mass will have higher displacement. That's what it says. However, between the masses there exists a point that does not move. This is called center of mass. So the center of mass of the system lies somewhere along the spring or somewhere along the spring, and the center of mass does not move during the whole process. It is important point to note that the center of mass does not move. It remains constant whether the two associated masses are moving with respect to each other. The center of mass concept is very important. We'll be using this center of mass concept frequently in our studies. Again, I am saying the center of mass is not at all moving when the two bodies are moving. In center of mass coordinate, the physical picture of the system changes from two mass connected. So this is a two body problem. We'll replace the two body problem to say single body problem. Now by doing that, we are getting rid of extra variables. Here the variables are there are many variables attached. What are the variables? m1, m2, they are constants, but for different masses or different bodies they will also vary, and x1, x2 are other variables. So to reduce the variables, generally center of mass coordinate is used in a physical problem. So physical is in the change of two mass connected by spring of force constant k to a single mass. So if we want to reduce the number of variables associated with a problem, we better to deal with center of mass coordinate system. Again, the center of mass is a particular point along the spring, and that does not change with respect to change in position of the heavier masses or lighter masses. So that particular point, in center of mass coordinate system, we use a quantity called reduced mass. It is the reduced mass is represented by mu, and it is derived from the individual masses. How it is derived, I'll just say now. So in general, when to simplify quantum or physical problem, when there are many number of variables are associated, generally center of mass coordinate system is used. With center of mass coordinate, we get information about the relative motion of the two masses with respect to one another, but and not their individual motion. So if we use a center of mass coordinate system to understand this particular system, two body system, we get a relative idea and not about the absolute motion of the two associated masses, that is M1 and M2. So center of mass coordinate system essentially gives about the relative motion of the two masses with respect to each other and not their absolute masses. Now why we choose to work with center of mass coordinate system? We are more interested in potential and kinetic energy associated with entire oscillator or as I said, the harmonic oscillator problem has a resemblance with the vibration of a bond. So generally we are more interested in finding out the potential and kinetic energy associated with the oscillator as a unit, as a single unit, and not their individual identity, or not the absolute motion of the associated masses. So in center of mass coordinate system, the reduced mass is given as m1 m2 over m1 plus m2, m1 m2 over m1 plus m2. m1 and m2 are the masses of body 1 and masses of body 2. Similarly, the center of mass, the position of center of mass is, to locate the center of mass, we have to use the expression m1 x1 plus m2 x2 over m1 plus m2. What is x1? The displacement of body 1 with respect to body 1, and x2 is the displacement of body 2. Now to this oscillator problem, to this classical harmonic oscillator problem, we will apply the Newton's law. In classical mechanics, Newton's law are obeyed. So according to the Newton's second law, mass is equal to force is equal to mass into acceleration. Now we are not using the conventional mass, rather we are using the reduced mass, because we are dealing with the center of mass coordinate system. So reduced mass into acceleration. And what is acceleration? Acceleration is change of velocity with respect to time. And what is velocity? The change of position with respect to time. So my acceleration becomes d square x over dt square. What is x? X is the displacement. Okay, then if I substitute these parameters in the Newton's second law, I am getting mu, that is reduced mass, m or mu a. Instead of a, I am writing d square x over dt square is equal to force. Now what is my force here associated with harmonic oscillator problem? My force is F is equal to minus kx. So I am writing mu d square x over dt square is equal to minus kx. If I rearrange, I am getting mu d square x over dt square plus kx is equal to 0. So this is a differential equation, and the general solution of this equation is given in equation 3, which says that the amplitude of motion or vibration with respect to time, that is xt, is equal to c1 e to the power I root over of k over mu t, c2 e to the power minus I root over of k over mu to the power t. Now this is a complex solution. So C1 and C2 are coefficients, and what is K? K is the force constant, mu is the reduced mass, T is time, and xt is the amplitude that depends upon time, amplitude of vibration that depends upon time. So this is a general solution of the harmonic oscillator problem. Now according to Eulers law, e to the power I theta, r e to the power I theta is equal to r cos theta plus or minus I r sin theta, or e to the power I plus or minus I theta is equal to cos theta plus or minus I sin theta. So I'll use the Euler's formula in equation 3. Now C1 is constant, it remains as such. Now for e to the power I root over of k over mu to the power t, mu t can be written as e to the power plus I theta. So e to the power plus I theta can be written as cos theta plus I sin theta. So cos theta plus I sin theta. Here my theta is root over of k over mu into t. Now similarly the second term of equation 3, C2 is a constant, it remains as such. here e to the power minus I theta, so that will be cos theta minus I sin theta. So if I open up the brackets, I'll be getting c1 cos theta plus I sin theta, c2 cos theta minus c2 I sin theta. So I'll be using another constant, that will be b1. b1 will be c1 plus c2. Similarly, I'll use one more constant, that is b2. b2 will be I root bracket c1 minus c2. So my solution becomes xt is equal to, what is xt? xt is amplitude of vibration with respect to time, or is it which depends upon time, is equal to b1 cos k over mu t plus b2 sin k over mu t, or I can say b1 cos theta plus b2 sin theta. So imposing boundary condition. Now to this to get a reasonable solution out of this reasonable understanding of this solution, we have to apply boundary condition. Now to apply the boundary condition, we'll use two conditions, that is at 0 time. At 0 time t is equal to 0. At 0 time the displacement is 0 and velocity is given as v0. So these are the two boundary conditions that we will be using, that is at 0 time t is equal to 0, displacement is 0 and velocity is also 0. So x0, t is 0 means x0 is equal to 0, that is the displacement is 0, that is the first boundary condition. Second boundary condition is v0 or velocity 0 is equal to, velocity is change in displacement with respect to time. So at time 0, velocity is v0. So I will apply these two boundary conditions to our general solution. Now in our general solution, this general solution, I will substitute this boundary condition. So I will substitute the first boundary condition, that is the position is 0. So my solution is what? b1 cos k over mu t plus b2 sin k over mu t. So here I will apply time is equal to 0. So for the second term, b2 sin 0, b2 sin 0 will be 0. So I'll only the first term will survive. b1 cos 0 is 1. So I'll be getting only b1. But according to boundary condition, x0 is 0. So my b1 is 0. So applying by applying the first boundary condition, I am getting that b1 must be equal to 0. If b1 is not equal to 0, then my first boundary condition will not be satisfied. So from first boundary condition, I am getting the information that b1 must be equal to 0. Now with this information, I will apply the second boundary condition. Again, the second boundary condition, the velocity at 0 time. Velocity is change in displacement with respect to time, and for time I will substitute 0. So d over dt, and xt I am writing. Now my xt has been reduced. From first boundary condition, I know b1 is 0. So this first term is going to 0. Now what I am left with? Only b2 sin k over mu t. So b2 sin k over mu t, and derivative of that means b2 root over of k over mu cos, derivative of sin theta is equal to cos theta. Now k over mu into t, again t I will substitute 0. So I am getting cos 0. Cos 0 is 1. So I am getting b2 root over of k over mu, and that is equal to v0, because second boundary condition says the velocity at 0 time is equal to v0. So if I rearrange, my b2 will be equal to root over of mu over k v0. So from first boundary condition I got b1 is equal to 0. From second boundary condition I am getting b2 is equal to mu over k v0. So if I put these constant values in my amplitude expression or displacement expression, what I am getting, the displacement with respect to time, or displacement of the bonds or masses with respect to time, is equal to only the second term is surviving. The first term is going 0 because b1 is 0. So b2 sin k over mu t. Now b2 is what? Root over of mu over k v0 sin k over mu t. So this is my solution of the harmonic oscillator, classical harmonic oscillator. The above specific solution is obtained when you impose the boundary condition. What are the boundary conditions? That at 0 time the displacement is 0 and the velocity is given as v0. Now as the sine and cosine functions are periodic in nature, they repeat themselves after a certain period. with respect to position and time, means they are oscillatory in nature. The period of oscillation means the period of oscillation is defined as T, capital T, and that is defined as K over mu T plus T, that is the oscillation period, minus K over mu T is equal to 2 pi, means every 2 pi, after every 2 pi angle, or after every 2 pi phase angle, the oscillation repeats itself. So this is the oscillatory condition, and from that oscillatory condition I can find out the period of oscillation is equal to 2 pi root over of mu over k, 2 pi root over of mu over k. So this is my period of oscillation. From period of oscillation, if I take the reciprocal or reciprocal of the period of oscillation, I'll get my frequency of oscillation. So my frequency of oscillation, the frequency of vibration of harmonic oscillator or frequency of oscillation is given as 1 over T. What is T? That is the period of oscillation. And what is T? We have obtained 2 pi root over mu over k. So if I substitute T value, I am getting my oscillation frequency. Frequency of oscillation is 1 over 2 pi k over mu, root over of k over mu. This equation 5 is important. This gives us information about frequency of oscillation. Frequency of oscillation or frequency of vibration of a harmonic oscillator. Now what is k? K is force constant of the bond and mu is the reduced mass. Now this equation 5 is important. Now the general solution that we have obtained, the general solution of displacement with respect to time was what? B1 cos k over mu t plus B2 sin k over mu t. When we applied the boundary condition, the first term vanished, only the second term was remaining. Before apply, we can also rewrite those this displacement expression, that is displacement with respect to time expression, k over mu, this k over mu t, this k over mu t can be written as 2 pi t over t, that is b1 cos k over mu t was there. So k over mu root over of k over mu is equal to 2 pi over t. Similarly here also for sine function 2 pi over t is used. Then angular frequency is also defined as omega is equal to 2 pi omega is equal to 2 pi nu. So 1 over t, the capital T, or what is capital T? Capital T is period of oscillation. So 1 over t is nu. So omega, the angular frequency omega is 2 pi nu. So this 2 pi nu can be 1 over t is nu, so 2 pi nu can be replaced as angular frequency. So my displacement of the harmonic oscillator, the displacement of masses associated with harmonic oscillator can also be written as b1 cos omega t plus b2 sin omega t. When we apply the boundary condition, this b1 term is going to 0. That's why the first term vanishes, only the second term survives. But before applying boundary condition, this is the general solution. Or equivalently, I can also write the displacement is equal to a sin omega t plus alpha. What is alpha? Alpha is the phase angle. So these three expressions are same as the expression, the general expression that we have written here. So the general expression that we have written here, this k over mu root over of k over mu t cos and sine root over of k over mu t is same as all the three expressions. And what is omega? Omega is the angular frequency, which is given as 2 pi nu. And what is nu? Nu is the frequency of oscillation, and that is given as 1 over 2 pi k over mu, and that is the reciprocal of period of oscillation t. Now what is the kinetic energy and potential energy associated with the oscillator? The potential energy we have discussed is given as half kx square. From classical mechanics, we know the potential energy is given as half kx square, and the kinetic energy of oscillation is given as half mv square. And instead of m, we are using the center of mass coordinate. That's why we will use the center of mass and the center of the reduced mass, and the reduced mass is given as mu. So the kinetic energy is half mu v square. Now kinetic energy and potential energy oscillate with respect to time. How this oscillates with respect to time, we'll see. Now there is a question: graph the kinetic and potential energy as a function of time and show that the sum of kinetic energy and potential energy is independent of time. So we'll derive potential energy, we'll derive an expression for kinetic energy, we'll graph them, both the energies will graph, and we'll show that the sum of kinetic energy and potential energy is independent of time. So first, potential energy, half kx square. Now what is x? X is the displacement with respect to time, and what is x? x value we have obtained, a sine omega t plus phi alpha. What was alpha? Alpha is phase angle. What was omega? Omega is angular frequency, angular frequency, and that is given as 2 pi nu. So instead of x, I'll write a sine square, that this is x square, so a square sine square omega t plus alpha. Now this k, the force constant k can also be written as mu omega square, because omega is also root over of k over mu. So k is equal to mu omega square. What is mu? Mu is what? And the reduced mass of the system. Omega is angular frequency. So my potential energy turns out to be half mu omega square a square sine omega t plus alpha. Similarly, my kinetic energy turns out to be half mu v square, and for v I will write dx over dt. Now what is my x? X is equal to a sine omega t plus alpha. Now here there is a differentiation you have to take. So if we take differentiation of a sine omega t plus alpha, because x is what? A sine omega t plus alpha. So if I take differentiation of x, that is a sine omega t plus alpha, I'll be getting a cos omega t plus alpha, and when I take differentiation, omega term will also come out of that differentiation, and I have to take square of that. So I have to take square, then what I am getting? Half mu omega square a square cos square omega t plus phi plus alpha. Now my potential energy is half mu omega square a square sine square omega t plus alpha, and kinetic energy is a square cos square omega t plus alpha. So my potential energy turns out to be a sine function, and kinetic energy turns out to be a cos function. So if I plot those functions, I'll get these periodic functions, that when potential energy is high, kinetic energy is low. When kinetic energy is low, potential energy is high, and they repeat periodically. So the sum of kinetic and potential energy is given as this dotted line. The sum of kinetic energy and potential energy is given as this dotted line, and that remains constant. With respect to time, the sum of potential and kinetic energy remains constant. So we will see this mathematically, that is the sum of kinetic energy and potential energy remains constant. Now we'll take potential energy and kinetic energy, and we'll take sum. So half mu omega square a sine square omega t plus alpha, half mu omega square a square cos square omega t plus alpha. If we do the sum, then we'll get a term called sine square theta plus cos square theta, and that becomes 1. So I'll be getting half mu omega square a square. Now there is no time dependent part here. Nothing is time dependent here, only omega is there, and omega is 2 pi nu. So generally this total energy is constant quantity. It remains constant with respect to time. It does not vary. The total energy does not vary. Only the kinetic energy and potential energy vary periodically. When kinetic energy is high, potential energy is low. When potential energy is high, kinetic energy is low. And at what position the potential energy is high? When we stress at the extreme position, at the highest displacement, we have only potential energy, and when the displacement is 0, we have only kinetic energy. So that is how it operates. Means at the extreme end of the oscillation or extreme end of the vibration, we have only potential energy, and when there is no oscillation, we have only kinetic energy associated with the system. Now there are few important points to note. That is, the sum of kinetic and potential energy is constant. The sum of kinetic and potential energy is independent of time. This is the case because because they are not varying with respect to time, because we are not adding any energy after they are stressed, or any pendulum. When the pendulum starts oscillating, we are not adding any energy, or not that energy is also dissipated due to frictional force. Means we are not adding energy, or energy is also not consumed by any residual force like frictional force. So that's why the sum of kinetic energy and potential energy is independent of time. The harmonic oscillator can have any positive value for total energy. So there is no constraint on the value of energy. So each value of energy is allowed for this total energy can have any positive value, the classical harmonic oscillator has a continuous energy spectrum. There is no discreteness associated with this total energy problem. So this is all about the classical harmonic oscillator. We have not introduced quantum mechanics yet. So in the next session we will introduce quantum mechanics to our harmonic oscillator problem. So with this I will stop here. Thank you.